group leader for group number 13, and we're going to be talking about the differences between combustion engines and electric motors in vehicles specifically. So here we broke the topic up into more subtopics to really break down the topic itself. So we're going to start with how electric motors work, specifically break it down into their specific parts, how it drives the vehicle itself, and everything like that. And then we're going to move on to gas engines and how they work. Again, the parts, how they drive the vehicle, and very similar to what we're going to explain for electric motors. Then we're going to go into the history of electric motors, starting from the very beginning to really small electric motors, really small power it's producing, to now companies like Tesla making extremely powerful, extremely fast vehicles, and how they are able to use these electric motors in the ways that they are using them. And then we're going to be talking about the history of the gasoline engine, where again we're going to start from the beginning to now and how they work, which vehicles really use that gasoline engine to make some good power and everything like that. And then we're going to be talking about the pros and cons of electric motors and electric vehicles specifically, and how they will be great with speed and power, but the range isn't so good, where my group will get very specific in that topic. And we're going to be talking about pros and cons of gasoline engines and how they can give you some great miles per gallon, but also great power, the drawbacks, everything like that. Then we're going to be talking about the differences between the two engines, where we're going to kind of bring everything together and talk about the main things that one can do than the other, and everything like that, kind of tie everything into one thing. And then we're going to be talking about other uses of the two motors other than vehicles, and other applications they're used in, and kind of indicate future technologies that you may see electric motors or other things like that in. And then the question we want to leave with you is, which motor do you think is better? Which one do you prefer? So the viewers that watch this video, that question will be left to you at the end when we cover all of the things about this topic. Which one do you prefer? Which one do you not prefer? And things like that. But that'll be it. That's the intro to our topic. So enjoy the video, and thank you for watching.
Hi, my name is Omar Vasquez, and I research how electric motors work. So to understand how they work, I first looked at them in their simplest form. And to create a simple electric motor, you need two permanent magnets, a metal rod, a metal wire, and a power source. So for the permanent magnets, they would need to have a south pole and a north pole. And with these items, you create a circuit, tying the wire around the metal rod. And when you turn on the circuit, it creates an electromagnet, which gives the metal rod a north pole and a south pole. And these poles are aligned with the south poles are aligned with the magnet south pole, and the north pole is aligned with the magnet north pole, which causes them to repel from each other and spin and rotate towards the opposite pole, which gives you this rotation, which converts electrical energy into mechanical energy. However, the problem with this is that the electromagnet remains at that state and it doesn't move anymore, so that's not really useful for a car. So what engineers had to do was they had to add pieces to this so that the electromagnet could continue spinning so that you can move a car. So an electric motor in a car is a lot more complex. It has brushes, a commutator, a rotor, windings, stator, and axle, and it needs a power source to power all of it. So the way this works is you have brushes carrying the current to the commutator, and what the commutator does is the brushes, whenever they sense a gap in the commutator, which is this rotating copper part right there, when they sense a gap, it tells the commutator to change the direction of the current, causing the current to go from negative to positive to negative. And what happens then is it changes the poles of the electromagnet, causing the north poles and the south poles to flip and making the whole thing rotate again, so that you get more of that rotational motion and so that you start creating torque. And that starts spinning the rotor, which is in the middle. And here you can see the windings, the red and blue copper wires that are wound around, and that's what causes and those two things create the electromagnet. And then here you have the stator, which are these two big magnets on either side, which are the permanent magnets, which you saw in the other simple example. And basically all this motion spins the axle, which is back here, which then spins the wheels and moves the car forward. And all of this is powered by the power source found in the middle of the car. And so these simple fundamentals, they can be scaled up to power an entire train like the ones in Japan, or they can be scaled down to power our toothbrushes. The possibilities are endless. So yeah, we can find it in every single one of these objects. And here are my sources for this research.
Hello, my name is Peter Pham, and I'll be presenting on how gas engine works. To start, what is a gas engine? A gas engine is an internal combustion engine that runs on a gaseous fuel such as coal gas, producer gas, biogas, landfill gas, or natural gases. These basic process of releasing energy from fuel and air mixture creates this massive energy which occurs within the engine itself. This is a big internal combustion engine that major corporation uses. How does a gas engine work? So gas engines are produced by 2-stroke cycle engines, 4-stroke cycle engines, and also a 6-stroke cycle engines. The 2-stroke cycle engine had little to reduce moving parts, so that it uses a lot of capabilities, but also have really strong power in a narrow space. The molecules and air of the gases comes into the intake. As that get compressed, it comes up with a rotational speed that creates a power band, which pushes out the energy that was created into moving the vehicle. To add on, a 4-cycle system uses what a 2-cycle system, but enhances the ability even more by having 4 distinct processes: intake, compression, combustion, and exhaust. Similar to the second one, the intake, this is the same ability while using the gas molecules, compresses it and create powers, and then makes a power stroke just like the second one, and it pushes out through the exhaust. But with this, the exhaust creates even more power, since the power of the exhaust is added to this one. A 6-stroke engine have all 4-cycle engines, but the one advantage is that it has increased fuel efficiency while reducing the amount of mechanical complexity, which is like adding more parts or creating more tights in the area. So a 6-stroke system is produce the same, more power with less fuel consumed. This first exhaust part right here, exhaust chamber, is a 2nd stroke. This is the 4th and this is the 3rd. The second one, like I said, had a spark plug that uses this to create the power. This intake is created with a molecule. The molecule enters this, and then as the combustion creates in this chamber, it pushes out through the exhaust and creates energy for moving. Similar to that, the intake of the molecule comes through here, gets compressed. The spark plug adds it power, makes it super stronger, and this exhaust pushes out as you moving. The 6-stroke is also the same thing, but it includes water. The steam power stroke makes it even more powerful with the included molecules. But this exhaust steam is then condensed so that the exhaust will be lighter and easier to increase the speed and leaving the energy out of the vehicle. There's two different type of engines: a spark plug engine, like you've seen variously from the slides that I've shown, and a combustion ignition diesel engine. A spark ignition gasoline has this spark in this top right here, which as the molecule enters, this spark is created to make fire and combust and to create energy. But while a diesel one, a compressed diesel engine, just uses an air only, just to create a spark, because through the air compressions, the air is compressed to make it super hot to shoot out energy. As you can see, this is the spark one with a spark plug, and this one controls with just the intake of the air. In terms of energy balance is very important for a vehicle to thrive. With thermal efficiency, a combined heat power and engine cooling. So usually thermal efficiency, so like that's the six stroke, thermal efficiency is using less fuel while decreasing the heat of the engine as much as possible. That's why combined heat and power is very important in these three strokes. The 6 will have the best combined heat and power, while the 2 will have the least heat and power. And engine cooling. Usually engine cooling is used with water or air, but in terms of the 6 strokes engine, the engine cooling will be used with water. And this formula right here shows the flow gas requirement of the gas engine in normal condition at full load. Q equal P over N times 1 over LHV gas, whereas Q is the gas flow in normal conditions, P is the engine power, N is the mechanical efficiency, and LHV is the low heat value of the gas. These are my references that I used to research and done what gas combustion is. So to recap, a gas combustion is like, it uses different type of molecules to create powers in the engine to thrive with the engine to go wherever it wants and produce energy. Thank you.
So, some history on electric vehicles is that the beginning of the electric motor and EVs is a topic that is debatable. One such place where people look to when considering the beginning of the electric motor is in 1828, when Hungarian inventor Ányos Esteban Jedlik created an electric motor and used it to move a model car. A picture of that model car can be seen over on the right side. It's rather small. And another starting point where people often look when it comes to the beginning of a electric motor is in 1835, American inventor Thomas Davenport created his own electric motor to power a model train on a small railway, which you can also see on the picture at the bottom. So the first few countries to start serious development of EVs were France and the UK. In 1881, Gustave Eiffel created what is considered the first electric car. A picture of that is over on the right. It's rather peculiar. And in 1884, Thomas Parker played a big part in the development of electrical transportation in London. And in 1887, William Morrison began working on an EV that was unveiled in 1890 in the US. It held 6 passengers and had a top speed of 14 miles per hour. And in 1899, the Legemias Contente broke the record for the fastest road vehicle, reaching a top speed of 100 kilometers per hour, or roughly 62.1 miles per hour. And between the late 1890s and early 1900s, EVs were very popular relative to the number of vehicles there were, with popularity peaking in the 1910s. During the 1920s, though, the popularity of electric vehicles started to decline, and that was a continuing trend till 1950s. But in the 1960s, when there was a gas crisis or oil crisis, electric vehicles saw some renewed interest along with the development of hybrid vehicles. So things like the lunar roving vehicle was an electric vehicle that was used on the missions to the moon. In 1997, the Toyota Prius was released, and that was the first mass-produced hybrid car. And in 2008, the Tesla Roadster was the first production electric vehicle to have a range of over 320 kilometers. And in 2010, the Nissan Leaf was released, which was the most sold electric vehicle until earlier this year. In 2014, Tesla began their first version of the autopilot feature, and 2017 the Tesla Model 3 was released, and since it's released it has become the most sold electric vehicle. And in 2021 the second generation of the Tesla Roadster is expected to launch, and it will launch as the fastest production car in the world by acceleration.
This is the history of gas engines. As early as the 17th century, there were experimenters trying to use hot, gaseous products to operate pumps. By 1820, an engine had been built in England which used hydrogen-air mixtures that were exploded in a chamber, after which the chamber was cooled, thus creating a vacuum that acted on a piston. The sale of these gas engines began in 1823. The engines were very heavy and quite basic, but they contained many crucial elements which were used later in similar devices. There were many attempts by engineers and inventors throughout the next couple decades, but none were successful. In 1860, a French man by the name of Etienne Lenoir created an engine that operated on illuminating gas. The Lenoir engine was a converted double-acting steam engine with slide valves that admitted gas and air and discharged exhaust products. The engine did not produce much power, and it only used about 4% of the energy in the fuel. Even so, hundreds of them were being used in Britain and France within 5 years, mainly for powering water pumps and printing presses. To the right is Lenoir's engine. In 1862, French engineer Alphonse Beau de Rochas successfully designed and patented a four-stroke cycle. He believed that this engine would be much more efficient than the two-stroke cycle introduced by Lenoir. Beau de Rochas was never able to actually build this engine, and for over a decade, a four-stroke engine would not appear. To the left is Beau de Rochas. In 1876, Nicholas A. Otto, a German engineer, built an internal combustion engine based on Beau de Rochas's principle. The four-stroke Otto engine had immediate success, and despite its immense weight and poor economy, nearly 50,000 engines were sold in 17 years. The Otto engine did not get manufactured in the United States until 1878, shortly after Otto was granted a U.S. patent in 1877. To the left is Otto and Otto's four-stroke cycle design. In 1885, two former associates of Otto, Gottlieb Daimler and Wilhelm Maybach, developed the first successful high-speed four-stroke engine. Along with it, they invented a carburetor, which made it possible to use gasoline for fuel. Daimler and Wilhelm used this engine to power a bicycle, which they named Reitwagen, or riding machine. This served as the precursor to the motorcycle. To the right, you will see the Reitwagen blueprint. Around that same time, another German mechanical engineer, Carl Benz, had built a one-cylinder gasoline engine. This engine was used to power what many considered to be the first practical automobile. The engines built by Daimler, Maybach, and Benz were all fundamentally the same as the basic gasoline engines used today. And here are the references.
Hi, my name is Neha, and I will be talking about the pros and cons of electric motors today. So, electric motors have become more popular throughout the years because technology is rapidly evolving, and they also have many benefits as opposed to gas motors. But while they have many benefits, they also have some negatives, so I'll go over those in the next couple slides. So first, we have the pros of electric motors. So the first one and the biggest one is that they're better for the environment, because fully electric motors, they don't have an exhaust system as gas motors do, which causes less fumes being released into the air, and that also leads to less pollution and fewer greenhouse gases and cleaner air. Another pro is that electric motors do not use gasoline, which is a non-renewable resource, and electricity can be a renewable resource because it can be powered by solar, wind, or water power. And then another pro is that they require less expensive and less frequent maintenance than gas motors do, which saves money because gas engines have to have frequent oil changes, and with an electric motor that's not needed. And then another pro is that they are quieter as opposed to gas motor vehicles. And then another pro is that they have a longer lifespan than gas motors do. So an electric car would run for much longer than a gas motor car would, which can save a lot of money in the long run because you wouldn't have to buy a new car. And then another pro is that they have a very wide range of operating speed and without needing gears, unlike gas engines, which do need gears to operate their full range of speed. And then we will discuss the cons of electric motors. So the first one is that they have a shorter range than gas-powered cars. So their mileage range per charge is very low as compared to a gas motor vehicle's mileage range. On a full charge, most electric models are only able to go 60 to 100 miles, with a small percentage of them being able to go 200 to 300 miles per charge, while a gas vehicle, on the other hand, would be able to go 400 miles with a full tank of gas. So another drawback is the charging time for the battery. So an electric motor battery can take up to a few hours to fully charge, while putting gas into an electric car, into a gas car would only take a few minutes. And then another disadvantage is that it can sometimes be difficult to find a charging station. But while electric cars are becoming more popular, charging stations, the amount of them is also growing. But if you're in like a rural area, it might be more difficult to find a charging station. And then the last one is that electric batteries need to be linked together into arrays. So basically they're a lot heavier than a gas motor would be, which adds extra pounds to the vehicle's weight. So for example, the battery pack in a Tesla weighs about 1,000 pounds, which greatly reduces the car's range. And that is the end of my presentation. So these are my references, and thank you.
Hello, my name is Nazli Akbari, and I will be presenting the topic of pros and cons of gas engines. So first I want to define what a gas engine is. A gas engine, simply put, is an internal combustion engine. This means that they use manual or manufactured gas instead of gasoline vapor. And here I just put a picture of one. So when understanding gas engines, it's important to ask certain questions when deciding between a gas engine or an electric motor. So things such as what the function of the vehicle you're about to buy is, where are you going to use this vehicle, what is the vehicle going to operate, and how long will it last, how much fuel will cost and how long it'll last, how much will parts cost and how often will it need to be tuned and checked, so on and so forth, with maintenance, operations, and technology. So beginning with the pros of a gas engine, we can understand that when initially buying a vehicle with a gas engine, we can expect lower prices compared to that of electric motors. This is just because electric motors are newer technology and safer for the environment. We can expect higher prices. And then low maintenance cost is due to the fact that replacement parts aren't as expensive. As I said previously, they're not as new as electric motors, therefore parts aren't as new and there aren't more of them around. And then lastly, better agility. This means higher speeds due to less torque needing to be distributed evenly around in different areas of the vehicle. So now the cons of gas engines, it's going to begin with the harmful emissions. So unfortunately, the US is responsible for 1.7 billion tons of CO2 emissions from gas engines, damaging our climate and atmosphere. Secondly, low mileage. This is due to a high demand of gas, causing an increase in gas prices. According to Jason Tate from the website It Still Runs, the average driver can spend up to $3,000 a month on gas, and that value continues to rise at a steady incline. And then lastly, the fuel source is another con to gas engines. Tate, once again from It Still Runs, states that 57% of oil Americans use comes from foreign countries where they change the prices and manipulate them. That leaves the home country in economic shambles where they get the oil from. And then here I have an image showing comparisons of gas engines versus electric, and it highlights the points made in previous slides about emissions, mileage, and then cost with a diagram of the two in a vehicle and how it would operate there. So here you have the combustion engine and then the electric motor. And then finally, here are all my references for the information gathered. Thank you.
Hello, my name is Nicholas Santiago, and for my topic, I'll compare gasoline engines versus electric motors and see how the differences result in different driving experiences. Gasoline engines are reciprocating engines where pistons move up and down in different cylinders. They in turn rotate a crankshaft that converts their vertical motion into rotational motion. This led to early internal combustion cars being very rough with high levels of vibration, but as more cylinders were introduced, greater precision and machining was available, and advances in engine mounts and dampers were made, this wasn't much of an issue. In comparison, the electrical motor doesn't reciprocate. Instead, it operates in a smooth circular motion more akin to a jet engine than a car engine. There is much more input lag in a gasoline engine. Hit the accelerator and a cable or a fly-by-wire mechanism tells the engine to open the throttle bodies. This allows the engine to ingest more air, which is measured by the oxygen sensors, and directs the engine to inject a proportional amount of fuel. This air-fuel mixture is then compressed and ignited. In contrast, an electrical motor receives an electrical signal and almost immediately begins to create rotational motion. In new efforts to be more efficient, gas engines are getting smaller and compensate with turbochargers, which adds another layer of input lag. There have been deep levels of research and development in recent decades to increase power output and also efficiency. Innovations like VTEC, direct injection where the fuel is injected directly into the cylinders, and recently variable compression engines have all moved the needle slightly for the gas engines. As for electric cars, designs feature alternating current or direct current or induction or permanent magnets. Sure, there will be continuing of enhancements, but the technological advantage that gas engine creators have enjoyed will be largely neutralized. The electric motor really levels the playing field. Electric motors also create much more power per weight than gas engines, making each wheel independent when driving. The attribute about electric motors that's most heard of is their instant torque. Here we have a chart showing hypothetical horsepower and torque curves as a function for RPM for both an electric motor and a gas engine. The electric motor rises up to near its maximum output immediately at 0 RPM and then falls off when it reaches a certain RPM. In contrast, the gasoline engine doesn't really start delivering its torque until about 1500 RPM, and it will continue to rise until it reaches its max output and then fall off. This is why cars have transmissions. In the case of the gasoline engine, the range where the output is optimized is limited, and the 5 or 6 or even now 9 speed transmission allows the car to continue to speed up while keeping the engine in this peak RPM range. In contrast, electric motors usually have just a single speed gear reduction. The motor doesn't just keep its max power output all the way down, it actually starts to drop off as well.
For this topic on the project, we have combustion engines and electric motors, uses other than automobiles. Some general quick fact history on electric motor. In 1834, the electric motor was used to power a small-scale printing press. It's the first time an electric motor was used. In 1907, a Chicago-based Hurley Electric Laundry Company created the washer, essentially called the Thor. In the 1920s, electric motors were used for refrigeration. Previously, refrigeration was used powered based on gases and cold goods such as ice and things of that sense. Electric motors are used for many different things other than today's popular news of electric cars. Motors have been integrated in the majority of today's common goods such as vacuums, toothbrushes, washers, and dryers. Electric motors propels today's society, and without them, the world wouldn't be as productive. Whether it's an AC or a DC motor, the electric motor is still a big integration in society. Electric motors make up the heart and soul of movement, whether it's an escalator, an elevator, garage door openers, or generally anything automatic. Even today's expensive luxury good of a Vroomba, which is essentially a motorized vacuum cleaner. Some quick fact history on combustion engines. The first combustion engine was around the 1860s. Around the 1876, the engine was industrialized and was called the Otto engine. And around 1939, the first jet aircraft used a combustion engine, essentially a gas engine. One of the most interesting things about the combustion engine was it was created on Dust Explosions was the first engine, and it was created by two people named Nicéphore and Claude Niepce. If anybody knows some general history about those two, they created much of the components of what would make up photography in the camera. It's a very interesting thing. But today's society, combustion engines are used basically on the balance of transportation, whether it's bus, plane, boat, riverboat, steamboat, and boiler systems use combustion engines. Other than that, most outside goods such as your common tools such as yard trimmers, lawnmowers, chainsaws, and most powerful things use combustion engines other than, gas cars. But more on the idea of electric motors are primarily used other than cars. So that is the conclusion of our mini series.